Hello, everyone, and good morning. Thank you all for joining, and welcome to our Alumni Talk series by GC Connect. Today, we will have an interactive session connecting with our alumni speaker, Dr. Aneeqa Sabah. The topic for today is a common man, nanotechnology. So to begin with, I'd like to invite Mr. Sanjeev Jaising, Director of Advancement and Alumni Affairs, to talk about recent initiatives and collaboration, and welcome our alumni speaker. Welcome, Mr. Sanjeev.
Thank you, Shreya. And first of all, a very warm welcome to Dr. Sabah. And also, I must say, Dr. Sabah, that I have visited your lovely campus in Lahore many times.
Oh, okay.
Yeah, together with some former presidents and also with Dr. Naveed Anwar, and I was very well taken care of on each of those visits. So welcome. And by the way, sorry that Dr. Naveed Anwar, Vice President for Knowledge Transfer, is not available because he has a very urgent meeting starting. It was scheduled at the same time with the President. So he sends his regrets, but gives you also a warm welcome. And also a warm welcome to all our alumni who are listening in, and also those who are on Facebook Live. I must say that this, I believe, is the ninth series of alumni talks, and what was started, several months back has become very popular and very interesting platform for the transfer of knowledge from our alumni in various fields. And it is also heartening that out of the 9, Dr. Sabah, you are the second female participant. So I think, Shreya, we need to increase this, to make it more equitable in the future. So anyways, welcome everybody, and also a warm welcome to Faye, who is our president of the AITAA Alumni Association. She is on her second term right now, and she has done a great job in getting the alumni from all over the world also more connected with AIT, and also thanks to the Dr. Naveed's good team of Shreya and Ashim and the others who work with him. I think this has become a very interesting sort of mechanism. Just very briefly, as you know, we started our classes last week, I think on the 5th of August. And it has been a kind of operating the classes on a hybrid mode, because as you know, given the current situation, about 60% of our students are overseas, and they have been given the teaching through our recently successfully raised modification of the smart classrooms. So through these smart classrooms, we are able to give the students almost the experience of him or her actually being at AIT and then being in the class. So I think we hope that the students over the coming months will get the chance to be able to come to AIT campus in Bangkok, and until then, they will do this hybrid mode. And also thanks again to Faye and the national chapter presidents. They are all willing, and their names have been given to those students in each of those countries, so that if they need any questions or they want some mentorship or guidance or advice, they can contact their respective national chapter president and then get whatever information they want. Because after all, we at AIT, we know that the most important component at our campus is our students, because without students, none of us will be here. So I think if we can give the students a good 2 years or PhD 3 or 4 year experience at AIT, then they will use that opportunity and then also think of helping AIT in the future. And also, like Dr. Sabah and the others we have had, they will all do well and be able to contribute to AIT this way as well. So I think Shreya will talk more about Dr. Sabah's CV and what she's doing. So without further ado, I think I'll give it back to Shreya to introduce our speaker. Thank you very much.
Thank you, Mr. Sanjeev. Now I'd like to invite our speaker, Dr. Aneeqa Sabah. Dr. Aneeqa Sabah is currently working as assistant professor in physics department of Lahore College for Women University. She was awarded for overseas scholarship for PhD degree in the field of nanotechnology. She has also published 14 ISI impact factor journals and have been involved in many projects. Her research interest areas include nanosynthesis and fabrication, bio-nanotechnology, self-assembly and self-organization, nanocommunications, colloids, and material science. So now let's welcome Dr. Shubha.
Thank you, Shreya. Thank you very much. First of all, Shreya, I want to do some request. Can you please allow me to record the presentation also? Please
Yes,
allow
please.
me to record this also. Thank you. Okay, thank you everyone. Thank you, Dr. Naveed Anwar, the Vice President for Knowledge Transfer, AIT, Mr. Sanjeev Jai Singh, Mr. Maria, the President of AITAA, and also the audience, because it's very early morning and they are here to listen to me. So very much thankful. Before going to start my presentation and the work that we are doing in the labs, I just want to share that I have spent a lot of amazing times in AIT. I learned so much from AIT, hospitality, the knowledge, of course, the degree, postgraduate from AIT, and lot of memories with the community from all over the world, social networking. So every one of you who are in AIT and the alumni from AIT, we all have spent a lot of good time. So thank you for this AIT and all the alumni team that I am here as an alumni speaker. I have chosen the topic Common Man Nanotechnology. Why I have chosen? Because whenever we are developing some technology or we are flourishing some technology, we should think first that what are the problems that common man is facing, because technology should be adoptable by the common man, because otherwise it is for no use. We need to solve the problems, we need to think about the problems, and then we go for the synthesis, for fabrication, and for the final product that is to be in the market for the common man. And secondly, I will also discuss that how this nanotechnology can go from easy approach to the practical approach. So let's start. On the global ranking of academic subjects since 2019, countries are participating in different ways to this upcoming technology. 5 countries claim approximately 61% of the world top 400 nanoscience and nanotechnology universities, like China and United States, are almost in the same 21 to 5%, 21.5%, whereas Germany and South Korea is approximately at the same, contributing to 7%, whereas the United Kingdom is at 4.3. But yes, the Asian countries like Pakistan, uh, and India and Italy, they are also participating in this era of the nanoscience and nanotechnology universities in low rank and low scenario, but yes, we are participating and we are there. So hopefully in the coming time, we will meet these concepts or these developments by China and the United States, hopefully. But it's a happy news, and that contribution of various continents in publishing the nano articles in the first half of 2019 is about 60%. Of the whole nano articles belong to Asian countries. It means it reflects the priority of production and promotion of nanoscience. So hopefully the gap between the fabrication and to the marketplace, we will hopefully fulfill this gap in the coming scenario or in the coming era, as compared to the European countries that have only 24% of their nano articles in 2019. Now, what is actually the nanotechnology and how it started? As the famous Sir Richard Feynman said, there is plenty of room at the bottom. The problem of manipulating and controlling things on small scale. So again, the problem of manipulating and controlling things on small scale. The important thing is a small scale related to the nanotechnology. Sir Richard Feynman said, I would like to describe a field in which the little has been done, but in which an enormous amount can be done in principle. This field is not quite the same as the others, in that it will not tell us much of the fundamental physics, but it is more like the solid state physics in a sense that it might tell us much of great interest about the strange phenomena that occur in the complex situation. So important thing, the strange phenomena in the complex situations. Furthermore, a point that is most important is that it would have an enormous number of technical applications. Otherwise, the nanotechnology cannot be helpful. So applications are important to get benefit from this technology. So after that, one may think that what is actually the nano? It is maybe a just philosophy, it is a big field, or just an academic discipline, or maybe the degree program, but the conceptual, or it may be an technology that is based on the size, and the most important that whether from this technology we are getting benefited or it is profitable. So these are a lot of questions that come into mind when we talk about nano, an evolutionary process, or a platform to go to go for benefits, to go for applications, to problem solving or problem resolving, or it is a science that is based on the size. And most important, an integrated technology, the small technology, like lab on a chip technology. So is it so? Scientifically, nanotechnology is a science, engineering, and technology conducted at nanoscale that is about 1 to 100 nanometer. So the typical definition is for the size range 1 to 100 nanometer, but actually the size matters. When the material go to the smaller level, to the smaller size, their properties dramatically changes. And when their properties dramatically changes, it brings into a big size. The important factor is surface to volume ratio increased. As you can see here, in a bulk, in a quantum wells, in quantum rods and wires, and quantum dots, we are finding that energy is continuously, density of states continuously going to the discrete values, to the discrete or pointable values like we can see energy levels in an atom. So we can constrain, we can confine our electron within the specific dimensions. We are able to confine them, these electrons, to participate in a confined dimension. From the bulk to quantum wells, that is the two-dimensional nanomaterials, and quantum wires or rods or fibers that are one-dimensional nanomaterials, and then zero-dimensional in which all the dimensions are in controlled confinement. There are a lot of examples from nature, from man-made. They are in the range of, sorry, let me do this in the actual. Okay, so things that are natural, for example, in the ant by approximately 5 millimeter, in the human hair approximately 80 to 120 micrometer wide, the red blood cells 7 to 8 micrometer, and similarly the DNA structure, it is 2 to 12 of nanometer diameter. These are the natural rings. So before the developing and flourishing, or nowadays, the big science of nanotechnology, nature already representing this nano to us. Things that are man-made, in which we can find the rods, the fibers, the carbon nanotubes, and self-assembled structure by using the different natural template also. We will discuss that what we are doing in the lab, so we will also go for it. Before the technology come into science, before the science come into the technology, we have to see that how this technology can affect our society. Nanotechnology have significant social impacts in the areas of military applications, intellectual property issues like copyright, the trademark, your product, as well as influencing the labor and balance between the citizens and governments. In National Science Foundation, a report was published in 2001 in a workshop that accelerate the beneficial use of nanotechnology while diminishing the risks. Of course, the dark side of technology or the risk should be lessened. Of course, each of things have positive and negative aspects. the negative things, but we have to develop things in the market or present the things in the market with the less risks. Improve the research and education, guide the contribution of key organizations. And the recommendations that have been mentioned after the workshop: make the support for social and economic research studies on nanotechnology a high priority. Include social science research on the societal implications in nanotechnology research centers, and consider creation of distributed research centers for social and economic research. And the most important, public participation. Build openness, disclosure, and public participation into the process of developing nanotechnology research. The public is very important. Public participation in how, what is the sense of this public participation? That the problem solving, we should know what the issues and what the problems in our area, in our country, in the world we are facing, and how our technology or our research can helpful to overcome this problem. Need to inform, educate, and involve the public. Create an infrastructure for an interdisciplinary evaluation of scientific, technological, and social impacts in the short, medium, and long term. And educate a workforce. Yes, the people, the students, the faculty which are working for it, they have to educate well for it. As an ethically responsible leaders, we must ensure that technology advances the human well-being and does not detract for it. And for this, we need the speedy technology adaptation, broadening the economic and social benefits, and accelerating and increasing our return on the investment. In the nature, we are finding so many patterns, like we have the lotus leaf effect, which is helpful for self-cleaning. I have also worked in the lab with my students and also doing my for the um, lotus leaf effect by using the concept of the lotus leaf effect, that is hydrophobicity and hydrophilicity, and this is used for the application of self-cleaning. We'll discuss it further. Gecko foot effect, that is sticking on the wall. They have special type of nanostructure that can help them for with the adhesive forces to stick on the wall. Water spider effect, dry through micro hairs with the nano ridges. They have special kind of nano ridges and hairs to be dry even in the water. And the spider silk, a strong nano composite that is used for bone tissues and engineering with the silica fusion. We have work also on the silica nanofibers. Will explain it further. So these are the examples from the nature, even the butterfly wings that show the radiation light film learning to make rainbows from the butterfly when the sunlight on it. So we can also use these wings as template to get the geometrical structure to design our nanostructures for high surface areas. Nano thresholds, nano spikes, nano ladders, nano ribs, whorls, these different kind of patterns we are finding in the nature materials. So nature already known that nature gives us nano far beyond we are here to describe it. The impact of nanotechnology, new and better nanomaterials, nanostructure, nanosystems, and they are helpful for us in different fields like information technology. We are getting more fast computer with the less power consumption. We are having the good energy and nanomaterials that are increasing the energy sectors, or they are responsible for cleaning the environment. We are also getting more modified textiles. The medicine industry is flourishing. Agriculture for finding the crop yielding, increasing the crop yielding, and also getting the better quality, the food safety, transportation. Nowadays, we are getting the vehicles with the nanomaterials or nanocomposite that are actually reducing the fuel problems. So hydrogen production, most of the Asian even countries side by side with the Europe working on the hydrogen production as a fuel, mechanical engineering and robotic systems. So these are all the technologies, these are all the fields where the nanotechnology is playing a very important role. The study, control, manipulation, and integration of atoms, molecules to form the material, structure, component, devices, and the system with uniquely different properties and behavior. So important is, due to the short structure, due to the small structure, due to the smaller sizes, we have different properties and behavior, which is important. So science and technology are always interrelated like chicken and egg. So they are both key factor for each other. The application of nanoscience, especially for industrial and commercial objective, theory and experiment, both are equally important. If you want to develop a something for the mankind, for the help of mankind, then theory and experiment are important. Now, nano may be easy. Somehow, for the synthesis point of view, there are two approaches, the bottom up and the top down in general. So in the bottom up, we are finding the smaller molecules that are built up or together by some forces to form the nanoparticles. From the smaller molecules, we get a new nuclei, and then we have a new particles. So synthesis and making of nanomaterials is cheap and cost effective by the bottom up approach. But when we go for another one, which is in comparison, that is top down, we have to go from the bulk, from the large to the smaller one. So it is little bit expensive in comparison because it needs some kind of equipment in comparison of the bottom up, which we can do in simple our synthesis lab. But somehow characterization is expensive, but for this we can sort out this problem by having some collaboration with some partners, maybe in our center which where we are working, or maybe from one to another center, or maybe with the countries, so that more and more research benefits we can get, or more and more collaboration give us a final product. The tools that can be used for characterizations are transmission electron microscope, atomic force microscopy, scanning electron microscopy, etc. And we need the good team members. If you have no manpower, if you have only the machines, we cannot do the work. So research is important with the mankind, with the man, with the equipments, and with the simple lab and equipment. The bottom up is the simple method, easy approach, and I am also working on it with my students. And I also have experience from AIT, COEN members, Center of Excellence in Nanotechnology members with the bottom up approaches. So I will discuss in detail with my work. These kind of experiments, or these kind of procedure involve techniques, anisotropic spontaneous growth, template direction, self-organization, sol gel, precipitation, and hydrothermal approaches. And the important is surfactant stabilized. What is actually the surfactant? These are actually the surface active agents with the hydrophobic tails and hydrophilic head, and they form a specific structures regarding to the specific concentration. These substances reduces the surface tension between the two liquids, or liquid and the solid. Their concentration matter to measure the efficiency of these salts or these materials. The polymers are also used as a surfactant. They actually use to stable the size of our prepared nanoparticle. They can also be acting as a reducing agent. So critical micelle concentration value direct the reaction and morphology of the reaction system, and we can get the structures like spheres, cubes, and rods. And as long as the structure change, the shape changes, we get the different kind of properties. For example, in if I talk about in advance or as beyond the range, so that we can say that in bulk we are with the insulator. One material is acting as an insulator, but when we go for nano, so it can be shifted to the conductivity. So this all can be done by simple bottom-up approaches, simply in the lab, by solving the problems of mankind. But equally important, I think the both are important, the top down and bottom up. But the first step can be the bottom up, then we go to the fabrication of devices, and then we go to the market. And between the fabrication of devices and the market, it can take years to go, because we need hit and trial methods to get exactly the same result after each experiment. From a synthesis point of view, from an organizational point of view, we need a both top down and bottom up. We need opportunities for to let them together, collaboration, the synthesis, and need representation for organization. We need bottom up and top down together. We need collaboration. The synthesis is mostly related to bottom up also, but if you have equipment and if you have labs and you can collaborate, then you can go for top down also. Equity, productivity, and sustainability is important. PMNT1, poor mass nanotechnology for the bottom-up synthesis, It was discussed from the point of view of scientists and engineers. It is a technology done with the minimal sources. By default, it is nanotechnology accomplished from the bottom up. PMNT1 conducted with the minimal sources. This phrase applies to the research and education programs in which the funding is scarce. The phrase is additionally applied to emerging enterprises that do not have in hand significant capital sources or government aid in the form of grants. Therefore, PMNT1 is the nanotechnology accomplished by seat of one's pants. It is therefore strategic and wise to conduct the bottom-up technology and partner with those that have PMNT1 needs big friends. If the countries have the problem, Asian countries, of course, facing a lot of problems for regarding to the water problems. So we need some filter materials, with some nanomaterials that can be used to filter out the contaminants, especially the arsenic from the water. And most of labs, most of persons are working on it and getting also success in it. So the important what we are doing in our labs nowadays, we have simply synthesized zinc sulfide and cadmium sulfide nanoparticles by traditional microwave radiations and sonochemical radiations under ultrasonic bath, and even our sunlight. So we got the different shape and structures, spherical and spike-like, needle-like nanostructures, and these nanostructures are helpful, for example, in different application of with high surface area for sensing. In the last picture from the right, you can see is the effect of sunlight, which is much better and homogenized in comparison of all other, because the microwave radiations are fast enough in comparison of ultrasonic. And if you go for sunlight, you just have to put the samples for some days, for some hours, without any disturbance. Then continuous irradiation affect their homogeneity. It was slow time process. So you can say it is simple to synthesize. Of course, it is first step. You cannot bring these particles to the market as it is, because it needs almost 30 years to for the particle to be in the market, by after again and again hit and trial method. It was done in my during my PhD, that biomimicry, living evolution. We have taken the concept of combination of natural material and our metal, the gold nanoparticles, and the fungi that grows almost our breads and something. So we got this fungal hyphae and we mix with the gold nanoparticles. We grow them together, and after their growth, we got these kind of structure, that is the hyphae, and the metal nanoparticles are deposited on it, so we get the gold wires. But right now, these are not like arranged mesh of wires. They are entangled among each other. So what we have done, under the scanning electron microscope, we can find these kind of wires, but when we, these kind of fibers, gold fibers on fungal hyphae. But when we go for, this is the schematic presentation, that it is the concept of self-organization of these gold nanoparticles on the template of hyphae, and they are forming the wires, or this is the forming a self-assembled structure. We just apply different kind of traits like light energy, like obstacles, and the electric. Try to we think to apply the electric field also, but it was not very successful. But the light gives a successful remedy or successful fabrication of these wires. And our purpose was to arrange them in a complete mesh of wires, instead of to remove their entangles, to remove their uh, entanglement. The controlled integration of microbial tropism and self-organization of gold nanoparticles revealed, aligned, and structured point-to-point biomimetic wires, because we copy the structure of biothings into our metal nanoparticles. And these were the structures observed under scanning electron microscope, and the reflection represent the presence of the gold nanoparticle. Some pictures are from simple optical microscope, and some pictures are from scanning electron microscope. You can see gold microwires of about 1 to 2 micrometer diameter and length exceeding 1 millimeter were grown with the maximum divergence of 40 to 50 from light path. When we are putting the light on them, they are diverging from 40 to 50%, regardless of the illumination color, and displayed wide variation in dimensions and morphology. Their conductivity was examined and diameter was measured, so they are found to be 2.5 into 10 power minus 8, 1 by ohm meter, so they were found to be conductive. Uniform and even distribution of destabilized gold nanoparticles on aspergillus niger hyphae was observed. The plasmon shifting in absorption peak of gold colloids during the growing microvirus were also observed in UV visible. The glutamate uptake, entropy, we are finding the different kind of forces between them, like entropy, hydrodynamic forces, Brownian motion, and hydrophobic interaction between fungal and gold surfaces assisted the self-assembly by organizing the gold nanoparticles on living hyphae. And the recommendation for all of you is that we can extend this to other stimuli by the combination of stimuli. I'm trying nowadays to do this first theoretically by simulation so that the results we got and then we can apply to the experiment. It is a multidisciplinary approach required for achieving the exact balance between the assembly and functionality of particles to integrate the devices on industrial scale, though big for though, a new way for implementing the integrated interconnection systems, light-directed metallic waveguide, hybrid channels, etc., the building of functional superstructure with high sensitivity towards electrical and optical properties, which is still a challenging era for this, because handling of bio things is difficult. Recently, we have worked on alkyl silica hybrid wires by using the natural and chemical surfactant, that is the green synthesis. The green synthesis is less hazardous because we are using a natural material from the biomaterial, which is not danger for us. And we use the simple sol gel technique. The lotus leaf was used, its extract was done, and then we have used the simple sol gel technique and we got hydrophobic layer. Lotus has hierarchical structure, hydrophobic, epigutiliary wax, COOH group, and amine group as the reducing agent. The self-cleaning property from the lotus effect. You can see that there are drops on the leaves. So it means that these water just move away the dust with it and not absorb on our surfaces. And the chemical in comparison used was CAT moss, octyl trimethoxysilane. It also shows a good result. The chemicals that were used, polyvinyl polymers, butanol, sodium nitrate, ammonium solutions, so simple that were available in the lab. We will use them because polymer is required for the long chain in order to make a surfactant, in order to make perfect sizes. And we also got thin films and membranes from it. The membrane gave better result than the films. The hydrophobicity measurement was done on the different glass slides on the cotton fabrics, and they give the better result for the super hydrophobicity if the contact angle between the hydrophilic surface and the other surface is less than 90 because we are two surfaces, the water surface, water drop surface, and our substrate surface. That may be the cotton cloth or maybe the glass slides. So theta will less than 90 though hydrophilic. If greater than 90 it is hydrophobic, and for greater than 150, then we have super hydrophobic. And all kind of these films were non-wetting, self-cleaning, low surface energy materials. The angle measure for glass slide 143 to 153, whereas with the cotton fabric it is 115 and 124 depending upon that concentration, because we also varies the concentration regarding to the substrate. And the silica membrane results was 139 and 150.4. The flocculation test was done to just see that whether there is the hydrophobic effect or not. So if we got the precipitation that are not dissolving in the water, so it means it is a colloidal effect. The contact angle measurement was done only by simple equipment, the optical microscope with the 3D cam, contact angle measurement with cellulose acetate filter paper, the glass, and the cotton fiber. So these kind of materials was actually the optical properties was also examined by UV visible spectroscopy, and this equipment is almost available in all of the labs and in institutes. So we can just find out the band gap and energy. You can see absorption peaks, and these absorption peaks, silica wires showed red shifting with an increased concentration From 10 microliter to 80, we have used two types of concentration of surfactant after hit and trial method and get the best result. The band gap was reduced and by increasing the concentration, and band gap range from 3.4 electron volt to 3.8 electron volt for the silica wires. Under scanning electron microscope, we are finding these kind of wires as we have designed by the simple sol-gel method. Chemically inert silica oxide shell prevents the lateral growth of silica wires, and thus the perpendicular growth of wires has shaped them into the bronze structure. It is obvious that silica nanowires consist of silicon core, dark in color, covered by the silicon oxide shell, which is bright in the color as you can see in this picture. So different concentrations simply surfactant on the different substrates, and simple sol-gel method was used to design these kind of films and membranes. These wires were evident on the coating of sample on the glass slides, and porous structure is actually the membrane structure. These kind of films can be used as a water repellent films in different industries. You can see on the window glass, on the glasses, on mobile screens. Even nowadays, these technologies are useful and in running in application in many countries already. But we are of course in a initial steps to design these kind of films. We need almost years to be to the industrial scale. And these membranes were tried for the osmosis by the osmosis for filtration, and we find that the salt rejection was approximately of 95.9%. For the silica membrane with this chemical CRT-MOS and silica membrane with this concentration, with a different concentration, they both rejected the salt in good amount. Of course, 100%, 95.9% and 96.98%. And permeation flux was 3.04 by meter square H, and the salt rejection was calculated by sensitivity meter by the permeation flux G. The separation process was calculated as uh, amount of permeate, that is how much is the permeation, and membrane area. It was dependent on the membrane area and also the time. It requires almost a long time, so this was actually the deficiency, and we are trying again to get this filtration. Of course, filtration was good, the rejection was good, almost 96% of the salt was rejected by using this osmosis process and this silica membrane that we have prepared in the lab, and we already have published this result. It is estimated that synthesized membrane can be used for application in water purification with accuracy, and these membranes can be made antibacterial for using in different fields of science and technology too. Other thing we have done is zinc sulfide nanostructure via surfactant medicated solution. We use different kind of polymers, and they were acting as a surfactants, and then by applying different conditions, stoichiometric control, surfactant accelerator directs the crystal growth, better reaction growth rate and crystallization we obtained by this method to prepare zinc oxide nanostructure by using these surfactant at different temperature. These polymers react with differently. TEA, triethanolamine, is a weak base due to their single lone pair of electrons attached on either nitrogen or oxygen atoms into their structure. They fit their position in the structure and used as a complexing agent with the metal, leading to the dissolution of zinc hydroxide into the zinc oxide. We got this kind of structure, the PEG, polyethylene glycol, and rods and whiskers, rod-like, plate-like flakes, and cauliflower-like morphology due to the surfactants are in the nano range, having the size range from 24 to 41 nanometer. Increase in concentration of surfactant and temperature will ultimately result in decrease in the particle size and agglomeration of particles. The average band gap measured was within the nano range of 3.39 to 3.68 electron volt and exhibiting the redshift. Increasing concentration and temperature of CTAP and PEG leads to the large particle size. Increasing concentration and temperature of TE leads to the decrease in particle size. So we differentiate some concentration and temperature, and we get the different sizes. So different sizes mean different properties. Optical properties were measured and redshifting was observed. Wide band gap as synthesizing sulfide nanoparticles can be used as high temperature operating devices or photonic devices. Similarly, in another aspect that by increasing the concentration of PEG, CMC value decrease as the long chain length of polymer affects the reaction system by decreasing the diffusion of PEG on the surface of metal oxide as increase in the chain length of PEG. So as long as the chain length is increases, this affects the reaction system by decreasing the diffusion. At low temperature, TEA molecules have enough time to bind themselves on the nucleating surface of zinc sulfide, and thus we have the uniform sized nanorods at the high temperature. The growth of nucleation increases due to increase in thermal energy of the system, consequently narrow the size of nanorods. So when you are differentiating the sizes, you are differentiating the structures, you are matching across with the different properties. Localization of, and they can be used for different or various applications. Localization of zinc acetate precursor on the micelles formation or surface was observed due to electrostatic interaction because it has the dual nature, positive and negative ions. So there is the electrostatic interaction between cationic micelles head and negative acetate ions. This was touched by anodic alumina. This alumina was also used as a template for a structure, but we have designed these alumina in our lab by ourselves, and these porous structure was obtained where by using three types of electrolytes: the sulfuric acid with the small diameter, oxalic acid the large diameter, and phosphoric acid the largest diameter. And by using three types of electrolytes, we just get the pores of alumina by using this simple chemical reactions as I've shown. This was the kind of membrane we get for alumina, and template was used under the observed under field emission scanning electron microscope, and pores are there. We get the porous structure. We were able to get the porous structure, and after the formation of oxide by the movement of aluminium ions migration into the electrolyte solution, the flow of oxygen ion is in the reverse direction. So by this oxidation and reduction process, we got this porous structure. This was the achievement. And then by getting this porous structure, we have also tried, instead of electrodeposition method, by simple soldier method to deposit some kind of metals on them by using hydrothermal solvothermal method, and we got nanorods and nano discs. Though we were not able to get the 90% of these structures, but we were able to get almost 60% of nanorods and nano discs onto these pores. And this is for the gold materials tried to deposit on these template that we have prepared simple in the lab. And secondly, silver nanoparticles were tried, but they were unable to get in the pore. So pore size actually mattered with your metal nanoparticles. Your metal nanoparticles and the pore size should be in matching so that you can get your materials inside the pores. But for the gold, we were able to get nanodiscs and nanorods. For the silver, it was not well defined, but we tried, and we get almost like cauliflower-like, flowers-like structure. This is the approach of quantum dots, multi-shell quantum dots caped with the polymer cadmium selenide, cadmium sulfide, and zinc sulfide core materials. And we got very good results by we observed very good results under scanning electron microscope with nanorods, nanoflowers, spheres. By adding the polymers, organic and inorganic ligands, we get one-dimensional wires in quantum regain. But for the simple cadmium selenide, cadmium sulfide, and zinc sulfide core, we were able to get the quantum dots with 7 to 16, 1 to 2 to 7 nanometer range. The core material was of cadmium selenide, and then there was a cadmium sulfide shell, and then there was zinc sulfide shell, and then the organic ligands. We have tried these materials, quantum dots, for the antibacterial activity, and we got very good result against the two bacterial approaches. We have go for PL spectra. We have the photoluminescence, and we get very good luminescence, approximately at 393 to 400 of peaks. The two pictures are there indicating that the first one, A, is just for the quantum dots and with organic and inorganic ligands, and the second one is we did a little bit experiment under the sunlight. You can see this one first. We have placed our quantum dots under the sunlight. We want to investigate the photochemical degradation happened in our dots. So band absorption and emitted wavelengths of 492 to 509 nanometer in cadmium selenide, cadmium sulfide, zinc sulfide polymer caped shell, multi-shell quantum dots before sunlight impact and after sunlight impact. And due to this degradation, we have observed that there is the incident photon was observed by cadmium selenide. Then there is excitonic transition for electron and holes. They try to recombine, and after recombination, they emit the photons, and their emissive properties were observed. Antibacterial activities were also examined against the two bacteria, Pseudomonas and Pneumonia. Pneumonia didn't give the best results, but we get good results from Pseudomonia, and there is we can clearly see the inhibition zone, and we find it very resistive. We also tried for two antibodies, and we find them completely resistive. For cadmium selenide, the inhibition zone length was measured approximately 18 millimeter, and for pneumonia is completely resistive. Cadmium selenide and cadmium sulfide, similarly for cadmium selenide, cadmium sulfide, zinc sulfide dots, and then with the different polymers, we are also find them as with the inhibition zone. If we go back to examine such, we also have Meyer simple dislocation density, strain, lattice parameter, full width are maximum, and we are finding that in case of double shell, the lattice strain at the interface is reduced, as the middle shell allows the suppression of strain due to small lattice mismatch between cadmium selenide core and zinc sulfide shell. We are keeping the band gap of cadmium selenide, that is the core, less in comparison of the wide band gap of zinc sulfide outer shell, because we want the electron to be confined within the shell, and there is a good lattice matching. When crystalline size decreases, the strain as well as dislocation density increase by increasing the shell growth, and then further decrease. Since the quantum dot were grown in a solution medium without any substance, the lattice contraction could mainly arise. The microstrain sudden increase and leading to either elongation or compression of the lattices. So this all was done only in the labs, only in the synthesis lab. The characterization was done within the home place, within our central lab, so students can do the research in a simple way, easy way for the common man. We have Meyer luminescence spectra. We are also finding a good absorption peaks within the range of 30 to 320 almost of nanometer wavelength, and then transparency beyond this. Band gap was simply measured. Cubic phase of these quantum dots was observed. The band gap showed the decreasing trend from as long as you go to the quantum dots and PEG. But when you add to organic and inorganic ligands, there is little bit increase, but this increase is basically we are coating the material, so increasing in the size of the band gap, but still they are in the quantum regime for the one-dimensional materials. They are diameter will be in the quantum regime. And Hindi. Just little bit look or glance on what type of research is commonly going on in the areas of the world. For the zinc oxide, simply you can see for zinc oxide, for health sector, for environment sector, for food safety sector, you can see zinc oxide, nano encapsulated oil, fabrication instrument, drug deliveries, all are used specially, or synthesis include the bottom up techniques. And the countries involving are Indonesia, Sri Lanka, Thailand, Pakistan. But with the high-tech technology, the China is leading to us for the diagnosing and imaging devices. The zinc oxide is used in antibacterial photocatalyst activities and sensing, nano-encapsulated oil in aromatherapy, anti-aging health supplements or medical industry health-wise. And drug delivery is related to China and Iran. These countries are contributing for anti-cancer therapeutics. Nanomembranes and nanoparticles related to the environment, as I have shown you, for the filtration process, though it was initial step. The bottom-up approaches, by using the bottom-up simple approach of nanotechnology for fabrication of heavy metals, fertilizers to clean water. Zinc oxide catalyst for bottom-up photocatalytic purification of water. Activated carbon includes some top-down approaches for used as a filter. Capacitive membranes, water desalination, nanostructure inorganic materials, again the bottom-up antimicrobial and eco-friendly packaging, enhanced nutritive quality and nano encapsulation. Then there is a food safety, again the metallic nanoparticles. We are also doing some now recent projects on matter doping for the zinc sulfide nanostructure, and they're also giving very high luminescence effects. But I didn't mention there because they are not completed yet. So antibacterial and fiber paints and food safety for by the help of silver and zinc oxide nanoparticle, biodegradable starches and clay for advanced food packaging. In case of agriculture, the bottom-up approach encapsulated fertilizer by using magnesium oxide, copper oxide, silica, zinc. They are using this for increasing the yield of the crop, for the quality, and for the encapsulated pesticides for crop control, carbonaceous or soils for to increasing the minerals in the soil. We can just we can just inject it, these materials, nanomaterials, into the soil to increasing the crop yield, to increasing the quality. Copper oxide is very good for the tomato crop. Nanoscale catalyst, zinc oxide and titanium oxide for dye-sensitized solar cells. And in case so in energy sector, battery and technology, again the China storage cell, catalyst, zinc oxide in hydrogen production. Thailand is leading. Graphene modification, though difficult to handle because graphene is two-dimensional material. High tech and high risks are involved, but still people are working on it. Hydrophobic nanoparticles for water resistance, anti-sweating clothes, zinc oxide nanostructure, silver nanoparticles, and silica nanoparticles as super hydrophobic, self-cleaning, antibacterial textile industry. And the last but not the least, electronic equipments, including both kind of synthesis, bottom up and top down, with the high technology equipments. China, Philippines are working on it. Printed electronic devices and microelectronic machines, microelectronics, mechanical devices. So it takes almost 30 years for new material to be discovered in the lab and developed in commercial products. So it's a long time to be the product in the market. But still we have to experiment, we have to do try hit and try methods to get to finish this gap between the industry. Designing a new material is a new territory. There is move away from hit and trial approaches and also a lot of error experiment you came across. These are some nanoproducts, nanomaterials, and nanoproducts according to different region of origin, and the nanomaterials that are in most demands, and nanoparticles according to the industry sector. We have to focus that what is required for health and fitness, home and garden, food and beverage, automotive, electronics, and others. And the materials that we are nowadays working, and most of us are working, silver, metals, silver, carbon, titanium, silicon, silicate, zinc oxides, different sorts of zinc, gold, nanoparticles. So these are the materials most in demand. And the region-wise, the nano products available, USA is at the top, 54%, East Asia 24%, Europe 50%, and others 7%. So as we are doing the papers, we are doing the research. So it means we can be in the product marketing also in some years ahead. Another important thing is a theoretical view. Side by side, to save the time to visualize the results before doing the experiment, for reducing the time and effort, simulation by various softwares nowadays is very attractive. Companies can save 10 times the effort and time required for experiment. Companies help you to buy new softwares like different console, Material Studio, NSYS, Aspantic to develop a new materials and then predict their macroscopic properties before doing the simple experiment. This is just a slide giving you some information that nowadays there is a situation of Corona, COVID-19. So we are just came across these kind of videos and also the many research upon it, that if the virus has genetic material, the lipid membrane and other proteins and spike proteins, then by detergent, how they can be removed. Because in the detergent you have polymers, you have surfactants, that is hydrophobic tail and hydrophilic head. And when the hydrophilic head and hydrophobic tail make bonding with these genetic materials, then like as they remove the dust, they also remove the virus. Hopefully, we will, any one of you or us will be able to develop such kind of material to remove this kind of things, or maybe can do a better research than this. So hope for the best. And the important thing is that drinking water, cheap energy, safe food, cheap efficient fertilizers, other products should need to increase the living standards of the people. Without those, without resources to afford such basic necessities is difficult, but we can do it if we are in the research process, if we do this by focusing, and we can do in a cheap environment, in a less in a simple environment with a simple synthesis in a lab, and we need some partners, of course. So but with the, we need to think about the consumers, we need to think about the people, that how they can get benefit. Instead of just looking on the positive side, I have just put one slide for the negative side need to focus. Nanotechnology has some shadow sides because still there are no recognized standards for producing and handling the nanomaterials. It is a new science and we do not know about its long-term effects of influencing the nanoparticles into environment. So we have to think about this also. Now nanotechnology is unregulated. Companies even do not have to label the products which contain nanoparticles. In fact, there are no recognized standards for producing and handling the nanomaterial. Many people are suspicious about the potential effects of nanomaterials. We have to see the potential effects that should be on our health, planet, and ecosystem, because it is a research that many generations to generation in animal and plants it can be transferred. We must have to stay informed about this new technology. People should share what they know with others. The more people know about nanotechnology, the more likely the manufacturers will take into consideration health and safety standards. So the summary is, for easy nanotechnology, it is a bottom-up. Bottom-up technology is not expensive. It can be done with the minimal forces. It is a low-tech technology. However, we need top-down partners, and common man nanotechnology we are doing in the lab with the simple resources are available. Simulations are there now to predict the results before the experiment and after the experiment. By including the industry funds, we can take the projects, we can work on it, experiment with the simple materials, we can do the process, devices, develop the devices, then we got whether we are getting the results, and then this results or these devices should try to be on the product development. Then we go for the commercialization. There is again we have to meet with the problems of competitiveness, because you are not only working on one field, there are so many people working on in one field, so maybe they are they are better than you to produce a product, and then the product will be in the market and leading you. So you should think about it also, that there is a lot of competition to make a product beneficial, to make a product develop, and to be a leader. So empowering bottom-up technologies and simulation is best for it to do it before getting the experiment, because during the simulation, during the theoretical approach, by different softwares, we can almost 80% we get the results. Though there is always some difference with experiment and theoretical results, but still we were able to get an idea that how we can mold our experiment. These are my research publications and book chapters I have written about nanovibers and nanovirus. Nanobotany in the book of Nanobotany, published in Springer in 2018. And recently I have also published a chapter related to the nanoagronomy on the base of agriculture. So, thank you. I acknowledge for Center of Excellence in Nanotechnology, Asian Institute, and my working department of Physics, Lahore College for Women University. Of course, my home ground, Punjab University, where I have done my basic knowledge, and the collaborators are Tech Islamabad, Chinese Academy of Science, and University of Gujarat. Always very thankful to all these partners. So thank you all audience, Vice President Dr. Naveed Anwar, Mr. Sanjeev, and Ms. Maria. Thank you so much. I hope I will be within the time.
Thank you, Dr. Aneeqa. Now I'd like to invite our participants to ask any questions or give some feedback. Please unmute your microphones to speak up. I have one question from the audience from Mr. Ghazal. How
Yes.
hydrophobic effect will help in case of COVID-19?
Okay, I have shown you this slide almost in the last, about this phenomena. You can also visit so many research nowadays going on. As in case of hydrophobicity, we have these surfactants with hydrophilic heads and hydrophobic tails. So these hydrophilic, when we make an aqueous solution that is in the water, the hydrophilic part make interaction with the water molecules, and hydrophobic part actually help to move away these uh, virus genetic material like it do in case of detergents. So like the hydrophobic head take away the dust particles, similarly it take away these genetic materials, and you can see in the right side picture they are making interaction with the genetic material. So basically we have to remove this genetic material that have to grow up for the viruses. Hopefully also you understand, or if any query you can ask again. They
We
form a structure like we have a missile in the picture. You can see they are forming a structure. They are covering the whole genetic material, and there is no other virus you can see in the last, where there are only the structure of hydrophobic and hydrophilic material.
Next, we have question
Okay.
from Dr. Bora.
Yes.
Yeah, thank you. Thank you, Aneeqa. So it's good to see you after so many years.
Yes, I know. Thank you so much. Good to see you
So
too.
for those who doesn't know, actually, we know each other. We did
Yes.
PhD almost at the same time together.
We were in the same department,
And
so
then
we have a good time there.
we are still continuing with the poor man's nanotechnology here. And actually, I
As
went
we
back.
have learned from this lab that nanotechnology, how we can use the nanotechnology for a poor man.
Yeah, so yeah, I think many of the work that you presented, I think similar type of work we are also doing.
Yes.
And very recent, like starting from this August, we have started a new program called Bio-Nano Material Science and Engineering, which basically you explain why the bio world is necessary to learn about nanotechnology.
Yes.
I think, yeah, this is a very good initiative also from the administration side, that they're bringing up all these alumni to share their ideas, and also I think it's a very good talk today. I don't have any question actually, but
okay, thank you. But I was
yeah, maybe
expecting
we
that
can
Tanujal, you will
continue
ask the
our
question,
discussion.
because Dr. Tanujal was always like that to ask different type of good questions. So I always enjoyed your questions.
No. I think
I
I'll
have
leave it
learned
to
a
the
lot from
students now, because
yeah. Okay, thank you.
I'll leave it to the students. But yeah, I
Okay.
still like that gold row, and thank you. You're continuing, because
Yes.
that is something. If people do not know, like the work that Dr. Aneeqa showed with the gold and the fungi,
Yes.
it was
And it was
actually started
yes.
from an accident.
Yes.
Some students were making the gold, and then they left it there without any. And then there was some kind of holiday, and after we came back, we saw some fungus on the gold colloid. So, but then instead of throwing, it was examined, and then we found something very interesting, and that's how that thing started. And Dr. Aneeqa, I think, did her PhD later, continuing that work.
Yes.
It's good to see you're still continuing.
Thank you, Dr.
Maybe we
Bharat.
can discuss and
Yes,
start
we
to do
can
something
discuss,
again.
of course, always.
Yeah, but the questions, of course, I'll leave it to the students today. I'm not going to ask anything.
Yes,
But just one thing, I think that the silica part, you mentioned the silica fibers.
yes.
So that also you are using the similar approach, using the fungi, or you are using a different kind of approach to make the fibers?
Not fungi, because in Lahore College of Women University, in the start, we don't have such kind of facilities regarding to bio. We have to communicate with the biotech department and something. So we just try the lotus leaves extract with the by the biofriend help, and we compare it with the use of the chemical. We didn't use the fungi.
Okay,
We
so
just used the
basically
green
you
part
extracted the
plant. Yes.
yeah.
Yes.
So you extracted
I
the chemical from the lotus leaf.
yes. True.
Okay. Yeah. So interesting approach. Okay, thank you. We will discuss later.
Yes, thank you.
Thank you, Dr. Bora. There is one more question from Mr. Patteride. Any example of startup business or service out of research at a university?
it's not right now. There is no such plan, but we are trying to get some project. So if we get some project, and then we can just start up right there. Still, there is just the initial research going in the labs at academic level.
Okay.
Right?
One more question from Mr. Dale. Concerning ethics with nanotechnologies, the US and EU have established regulatory frameworks, but for developing countries, what is your recommendation on how we can create awareness and lessen policymakers' apprehension to optimize technology transfer?
Can you repeat the question again?
Yeah, sure. Concerning ethics with nanotechnologies, the US and EU have established regulatory frameworks, but for developing countries, what is your recommendation on how we can create awareness and lessen policymakers'
regarding to developing countries, right?
Yes, regarding to
developing. As I have shown you that in the developing countries, still we are far away from it to create the policies, but we can think about it that first of all, we should be aware of in order to take some project or in order to start some business or something to go to the industry, we just have to sort out the issues and problems that the common public is facing, right? And if you got that, okay, by this research you can solve this problem until the market level, then you can design the policies and you can create awareness. In order to create awareness, you can just ask from the common public that what actually problems they are facing, on how we can solve them, how they can think that, okay, these things we require, yeah, these things we require, we need this kind of water purification, we need this kind of economically we are not stable in that matter. So for this, we have to go far away yet, right?
Thank you. Any more questions? We'll take the last question for today. Any more questions from the audience? Okay, so thank you everyone for sharing your ideas. Now I'd like to invite Ms. Maria Fey Niostro-Ferriols, President of AIT Alumni Associations, for the concluding remarks. Welcome, Ms. Fey. Ms. Fey, you will have, okay. Ms. Fey, we can't hear you. Can you unmute your microphone? Yeah.
Okay. Yeah. Okay. Thank you. Good morning, AIT family. In behalf of the Asian Institute of Technology Alumni Association, our AITAA Governing Board, our AITAA Headquarters Executive Committee, and our AIT alumni spread all over the world, we sincerely thank our alma mater, the Asian Institute of Technology, for co-organizing with AITAA this forum that gives opportunity for our alumni to share their knowledge and expertise in their fields of competence and proficiency. During this time of pandemic, when most of us are required to stay home, the challenge is to find ways and means where to channel our normal boundless energies. We are used to multitasking highly stimulating activities. Then suddenly, we have to apply our brakes. From macro, we need to go micro, and now even nano. Should we wonder that the science and art of nanotechnology started at the same time when AIT started in 1959? Here's the story from our Google search. The ideas and concepts behind nanoscience and nanotechnology started with a talk entitled "There's Plenty of Room at the Bottom" by physicist Richard Feynman at an American Physical Society meeting at the California Institute of Technology on December 29, 1959, long before the term nanotechnology was used. And it continues. Although modern nanoscience and nanotechnology are quite new, nanoscale materials were used for centuries. Alternate size gold and silver particles created colors in stained glass windows of medieval churches hundreds of years ago. The artists back then just didn't know that the process they used to create these beautiful works of art actually led to the changes in the composition of the materials they were working with. So, what do we do during this pandemic? I would like to thank Dr. Aneeqa Sabah for opening our interest in nanotechnology and its development and uses, and more on their practical application nearer to us, our place of work, and our homes. When we are challenged to master the art of doing nothing while we wait for the end of this pandemic, we can turn to the uses of the littlest of things. And as usual, we can discover the more innovative uses of the smallest particles of creation. This is a challenge and an opportunity for us, AIT alumni. We can follow through with what Dr. Aneeqa Sabah has presented. Maybe we can go back to its initial uses, paint our drinking glasses and glass windows into works of art, like the stained windows of the glorious heritage churches, or contribute to the longed-for solution of defeating the very, very small virus called COVID-19, or develop non-porous barriers to penetration of various small viruses into our systems. These may be possibilities. And so, may I invite our AIT alumni to contribute their knowledge and talent in these trying times. As mentioned by Dr. Aneeqa, the more we share about what we know, the better for us to address the possible negative effects of nanotechnology. Let not this pandemic hinder us in sharing our resources to continue innovating for our communities. Thanks again to all the organizers of this event, led by Dr. Navid, Mr. Sanjeev, and Ms. Rhea, and most especially our excellent resource speaker, Dr. Aneeqa Sabah. This interesting session will be aired in our YouTube channel, Walk the Talk AITAA, and our Facebook pages. So please subscribe to our channels. There will be more. Stay tuned and keep safe. May God bless us all. Thank you.
Thank you, Ms. Faye, for sharing your views. And thank you everyone for joining our live sessions today. A special thank you once again to our speaker, Dr. Aneeqa Sabah, for the wonderful talk. Hope to see you all soon with our next interactive alumni talk series. And please send in your feedback on today's session through email or our social media group. Stay safe and connected. Thank you everyone, and bye-bye. Thank you.
Everyone, stay safe.
Bye-bye.